So I want you to take a look at these two events here, two compound events. At first glance, they look very similar, right? They both involve doing something and getting the same thing twice. Okay, but there's an important difference here if we drill down into these a little. The first one, if I split it up into its two simple events, is you draw a queen, give it to a player, and then you draw a second queen. The second one, on the other hand, is you flip a coin, get heads, then you flip the coin and get heads again. Okay, so we think of these in terms of probabilities, right? The probability of getting a queen, according to our conditional probability rule, is the probability of a queen times the probability of a queen given that the first card was a queen. Over here we get the same thing but with heads. Yeah, now, here's the key difference between these two. With the coin situation, the probability of getting heads, given that the first toss was heads, is still a half. It's still just the probability of getting heads. That first toss doesn't in any way impact the result from the second toss. Or on the other side, for example, the probability of drawing that second queen, it's not the probability of drawing a queen because we didn't put the card back. Right? So the number of cards in the deck changed. Okay, so this intuitively is what we mean by independence. Right? Two events are independent if one of them occurring doesn't affect the probability of the other occurring. And that's fine, just intuitively. But let's see if we can be a little more mathematical about it. So I'm going to work this same scenario here. We could have done it with the cards, but the coins are easier because there's less options. So I'm going to define my two events. A is you get heads on the first toss. B is you get heads on the second toss. And I've just listed out my sample space. Right? Those are the only four possible outcomes of tossing a coin twice. So from this, we can see that these two probabilities are the same. There are two out of the four ways get heads on the first toss, that's a half, and 2 out of the 4 ways get heads on the second toss, also a half. Okay, so now let's look at the conditional probabilities. Right, the probability of A given B is probability of A and B divided by the probability of B. Well, the probability of A and B is heads and heads. There's only one of the 4 outcomes that gives us that. So this is 1/4 divided by 1/2, which is 1/2, which you'll notice here is also the probability of A. Okay, so hold on to that. I'm going to do it the other way around. What's the probability of B given A? Well, that's the intersection of A and B, so it's the same in the numerator, but the denominator changes. The denominator is now the probability of A, but the numbers are the same. This is still 1/4 divided by 1/2, which is 1/2, which is, you'll notice, the probability of B. Okay, so here's how I'm going to put these together to get our definition of independent events. Okay, the probability of B is equal to the probability of the intersection of A and B divided by the probability of A. What I did there is I took the probability of B given A formula, so that's kind of the second column, and I replaced the probability of B given A with the probability of B, just straight substitution. Now, if I clear the fraction, if I multiply both sides by the probability of A, we get this. The probability of A and B is equal to the probability of A times the probability of B. And this is going to be our formal mathematical definition of independent events. And that's what I've got here, right? If A and B are events in a sample space, then we say that A and B are independent. This is a definition. If and only if the probability of A and B is equal to the product of the individual probabilities. Okay, so we haven't talked about a lot of theorems in this probability section. So I do want to talk about one here that's kind of interesting. Suppose A and B are independent events in a sample space. Then A and the complement of B must also be independent. Okay, so how can we show this? Well, we need to show that the probability of A and B complement is equal to the probability of A times the probability of B complement. That's just our definition, and at this point, that's the only thing we've got to work with. Okay, so where I want to start off with is flashing back to our set theory conversation. The intersection of A and B union with the intersection of A and B complement is A. If you don't believe me, awesome. You can do a quick set argument, and you should be able to see this. So what I'm going to do now is I'm going to look at the probabilities of these two events. Right, the probability of the left side, because the two ands in the parentheses are disjoint, we can use our probability rules and make that the sum of the individual probabilities. That's the middle probability here. And that equals the probability of the right side, the probability of A. Okay, so what I'm going to do now is I'm going to solve this for that intersection, because remember, that's what I need to show something about. So I'm going to subtract the probability of A and B from both sides. All right, now, because A and B are disjoint, I'm going to replace that and probability with the probability of A times the probability of B. Now let's do some factoring. I'm going to pull the probability of A out. This becomes the probability of A times 1 minus the probability of B, and now we'll use a complement rule. 1 minus the probability of B is the probability of the complement of B. And that's what we needed to show. Right? That's what we needed to show to prove the original claim. Okay, so we're going to switch directions just a little bit in the next lecture. We're going to talk about something called expected value. Right? You can think of it as the average result that we expect to get if an experiment is done over and over again a really, really large number of times. And this is a topic that has a particular application for those of you who are kind of computer science oriented. That's a technique that you would use in the analysis of algorithms to show, for example, something that's called the average runtime of an algorithm.